Alright, y'all, today is one of the most exciting days of the whole year of chemistry. We are going to put everything together and be able to come up with a prediction of whether reactions will spontaneously happen using something called Gibbs free energy. So your can-do statement is, I can determine if a reaction can proceed spontaneously using Gibbs free energy. What is this Gibbs free energy all about? We know that many, but not all, exothermic reactions occur spontaneously. Those are the reactions with negative delta H reaction. We also know that many spontaneous reactions involve an increase in entropy of the system, a positive delta S system, but some processes that occur spontaneously involve a decrease in entropy, such as two atoms of hydrogen gas forming a hydrogen molecule. It would be extremely useful to us if we had a way of looking at a chemical equation and knowing ahead of time, without doing the experiment, if it would occur spontaneously. How can we do this? Well, this is where the second law comes in handy. Remember, the second law applies to all spontaneous processes, always. It says that delta S universe must be positive for a process to be spontaneous, aka thermodynamically favored. Our law again is that the change in entropy of the universe equals the change in entropy of the system plus the change in entropy of the surroundings, and that has to be greater than 0. But we know how to calculate the change in entropy of the system that we did last class with Hess's law in the standard entropy tables. But how are we going to calculate the change in entropy of the universe, the whole universe? Like, how is that even possible? And how are we going to calculate the entropy change of the surroundings? Well, in a chemical reaction or phase change at constant pressure, the only change that the system makes to the surroundings is the heat it transfers. That's the enthalpy change, or Q equals negative delta H reaction. So the system could do work. It could do work pushing back the surroundings, but remember, this is factored into the enthalpy change, so we don't really need to think about it. So using the definition of entropy, delta S equals Q divided by T, heat transfer divided by temperature, we can substitute to find the entropy change of the surroundings. Delta S surroundings equals the enthalpy change of the reaction divided by temperature. And we put a negative sign on that enthalpy change of the reaction because, say, the system is giving off heat, well, the surroundings then gain the heat. So the surroundings are opposite of the system in sign. We can plug that delta S surroundings equals negative delta H reaction over T back into the second law where we had delta S surroundings. So now we're working on our law a little bit. We have delta S universe equals delta S system minus delta H reaction divided by temperature, and that has to be greater than 0. So this is still our second law. Let's work on it a little bit more to make it more user-friendly. We can multiply both sides by negative T. So negative T delta S universe equals negative T delta S system plus the delta H reaction. And because we multiplied both sides of the equation by negative, now we have less than 0. Finally, so we don't have to be multiplying the entropy change of the universe by T every time we want to do a calculation, let's just call this T delta S universe, let's just give it a whole new name. Let's call it delta G reaction. And it's not negative delta G reaction, it's delta G reaction. Okay, so we have our new version of the second law. Delta G reaction equals delta H reaction minus T delta S system, or T delta S reaction. And that has to be less than 0. This is the most important law in chemistry, from my opinion. This is called the Gibbs free energy version of the second law of thermodynamics. And let's look at it again. Delta G reaction equals delta H reaction minus T delta S reaction, and for that to be spontaneous, that amount has to be less than 0. Again, remember, we just did some math and some substitutions. The delta G reaction is really just the T delta S of the universe. The delta H reaction is the T delta S of the surroundings, and the T delta S reaction is the T delta S of the system. We still have our second law. And that delta G of the reaction is called Gibbs free energy. We're going to talk a lot about that. Josiah Gibbs was a scientist, and he was the one who coined this term. So we have our second law of thermodynamics. with everything in terms of the system, and we can measure changes to the system. Now we don't have to worry about measuring the entropy of the universe or measuring the entropy of the surroundings. So let's look at these consequences. First of all, the way that the law is less than zero, the way we have a spontaneous process, is that the reaction is spontaneous when delta G reaction is negative, when delta G reaction is less than zero. Also, because we have T inside of the delta G, we can say that the delta G reaction is different at different temperatures. Okay, so it's definitely dependent on temperature. Next, whether or not a reaction will take place spontaneously depends on three things. First, the enthalpy change, delta H reaction, whether or not it's endothermic or exothermic. Also, the temperature. And third, the entropy change, the delta S reaction. What else? Well, G is a state variable since H, T, and S are state variables, and they are the ones that are contained inside the law. Just like we have delta H naught and delta S naught, the standard enthalpy and the standard entropy, we have a delta G naught, and that is the standard Gibbs free energy. The conditions, just like before, are 1 atmosphere, 1 molar if it's a solution, and 298 degrees Kelvin. That is SATP. I just want you to note that in real life, we usually don't use concentrations of exactly a molar. 1 molar is pretty concentrated actually for a lot of things. So we actually have an adjustment to find the actual delta G from like the concentrations that we do have and the standard delta G naught. And we'll cover that much more in the equilibrium unit. Next, delta G is only meaningful when the pressure and the temperature of the surroundings remain constant. Remember, that's part of the requirement for enthalpy change. But this is how we do experiments in the lab. Everything's open to the atmosphere usually, so we have constant 1 atmosphere of pressure, and the beginning and ending temperature is room temperature. So the reaction can give off heat or absorb heat, but then we're looking at the surroundings here. So overall, the temperature of the room doesn't change after the heat has diffused away from the reaction. Remember, we call G Gibbs free energy after the scientist Josiah Gibbs. And the definition of G is that it's equal to H minus Ts. Because we're usually concerned about changes, that's why we have our second law as delta G equals delta H minus T delta S. Note that we can calculate the delta G formation from tables of delta HF and delta SF. And if we have a negative delta G, we call that exergonic, or endergonic if it's a positive delta G. So this is key. What is this delta G business? Well, delta G is the part of the enthalpy change that does not become entropy. So if we rearrange our equation, before we had delta G equals delta H minus T delta S. Well, if we add T delta S to both sides of the equation, now we can have delta H, the enthalpy change of the reaction. Part of it is delta G and part of it is T delta S. T delta S is the part that's degraded as entropy. This is the energy that just goes out and diffuses into the universe, the energy that's spread out. But the other part of the enthalpy change is delta G, and this is the maximum amount of energy that could be freed to do work. And this isn't the pressure volume change work that we were talking about, like when we were talking about moving the atmosphere or gases expanding. This is the part that could do other work that we find useful. So it could be electrical work, it could be osmotic work, it could be muscle contractions or nerve impulses, all the other things that reactions can do. One key thing is that this isn't a conserved energy. It's not like energy that's not created or destroyed, so it's not actually energy. So some people are calling it now the Gibbs function. But basically, this looks at whether or not a reaction is likely to take place. So pretty powerful stuff, right? Like, now we know we can just look at a reaction and say from a thermodynamics perspective, will this happen spontaneously? If it doesn't happen spontaneously, we might as well not even investigate it. Next up, let's do some calculations. So, just like we were able to use Hess's law for enthalpy and entropy, we can use Hess's law for Gibbs free energy. It looks exactly the same. We just add up the Gibbs energy of formation for the products and subtract it from the Gibbs energy of formation of the reactants. One thing that's pertinent to know is when you look at the reference tables, you have to remember that usually the enthalpies of formation are given in kilojoules per mole, and the entropies are given in joules per mole Kelvin. And the Gibbs energy of formation is in kilojoules per mole. So a lot of times you have to convert entropy from joules to kilojoules. Let's do an example. Given the reaction hydrogen cyanide gas combining with hydrogen gas producing methane gas and ammonia gas. First, let's calculate the delta H reaction, the enthalpy change of reaction. This is very familiar. We have done this many times. Our original Hess's law. I went ahead and wrote out Hess's law for us. We have the delta H of the reaction equaling the heats of formation of the products minus the heats of formation of the reactants. Note that I multiplied the heat of formation of hydrogen by 3 since there are 3 moles of it in the reaction. I went ahead and put in all the numbers for us. One thing to point out is that the heat of formation of hydrogen is 0 kilojoules per mole because that is the element in its natural state at standard atmospheric temperature and pressure. When we put all these in our calculator, we get that the standard enthalpy change of the reaction is negative 256.0 kilojoules per mole. So this would be an exothermic reaction. Now, without looking at the numbers, would we expect that the entropy change of the reaction would be positive or negative? Why do you think so? So I'll give you a second to think about it. All right, so the key here is that we have all gases in our equation, and remember that gas molecules going all over the place are energy carriers, just spreading their energy love out into the universe, and the more energy carriers we have, the more entropy increases, or the fewer energy carriers that we have, the less entropy that we have. So let's look at the amount of moles of gas molecules on the left side versus on the right side. On the left side, we have 1 mole of HCN and 3 moles of hydrogen, so we have 4 moles. Whereas on the right side, we just have 1 mole of methane and 1 mole of ammonia, so only 2 moles. So if we go from 4 to 2, that's a decrease in the amount of energy carriers. And so we would expect our delta S reaction to be negative. We said that we expect that there's going to be a decrease in entropy because there's a decrease in the overall number of energy carrying gas molecules. Let's go ahead and prove it with some entropy calculations. I went ahead and wrote the entropy formula down on the screen. We're using the same rule as we did before, and we're just going to subtract the entropies of the products from the entropies of the reactants. I plugged in the numbers for us, and when we finally put everything into the calculator, we get that the entropy change for the reaction is equal to minus 214.8 joules per mole Kelvin. And because we have that negative entropy change, we know that entropy has decreased just like we thought it was going to. Now, we have opposite results. From an enthalpy change, we think that the reaction will probably happen. It's exothermic. But from an entropy change perspective, we think that the reaction is not going to happen because entropy decreases. Well, this is the beauty of Gibbs free energy. It looks at the contribution of each, and then finally delta G will tell us whether or not it will be spontaneous. So let's calculate delta G reaction at room temperature using the formula delta G equals delta H minus T delta S. Let's put our numbers in from when we found the enthalpy change and the entropy change. We had our enthalpy change as negative 256.0. We're going to subtract T delta S. Our temperature was 298.15 Kelvin, and our entropy change was minus 214.8 joules per mole Kelvin. And of course, we have to multiply that by 1 kilojoule over 1,000 joules to get rid of those joules and get us into kilojoules, so that everything's in the same unit. When we put the results into our calculator, we get that delta G reaction is negative 192.0 kilojoules per mole. And because we see that big negative sign there, we know that our reaction is spontaneous, at least at 298.15 Kelvin. We calculated the Gibbs free energy change above using the delta G equals delta H minus T delta S formula. But remember, Gibbs free energy is a state function, so we can use Hess's law on that as well. I went and wrote the Gibbs free energy equation for Hess's law, subtracting the free energies of formation of the reactants from those of the products. And let's put the numbers in from the tables that we can look up of Gibbs free energies of formations. One thing to observe, remember we have to multiply the hydrogen values by 3 since the equation has 3 as a coefficient in front of the hydrogen. And also, just like the enthalpies of formation of the free elements at SATP, the Gibbs free energy of formation is 0 kilojoules per mole of hydrogen. When we put that into our calculator, we find that the Gibbs free energy change for the reaction is negative 191.7 kilojoules per mole, which is the same answer we got as the previous way that we did it with the delta G equals delta H minus T delta S equation. So it really doesn't matter which one we use. The other one took 2 steps to find the enthalpy change for the reaction and the entropy change for the reaction. And this way we looked it up directly from the Gibbs free energies of formation. So whichever method you choose probably depends on the information that you have at hand. Remember, we said that one definition of Gibbs free energy is the portion of the enthalpy change, or the maximum amount of energy that can be freed to do work, like electrical work or osmotic work or nerve impulses, muscle contractions. Here the question asks, what's the maximum amount of work that can be done if 1 mole of hydrogen gas is used as the limiting reactant? Well, we just found that the delta G for the reaction was 191.7 kilojoules per mole. But that was when we had 3 moles of hydrogen gas. If we just have 1 mole of hydrogen gas, so we just have to multiply that amount by 1/3 of a mole. The moles cancel, and we get the maximum work is 63.9 kilojoules. The next question asks, how much heat will be produced if the maximum work is done when 1 mole of hydrogen gas is used as the limiting reactant and the reaction is carried out at room temperature, 298.15 Kelvin? Well, remember that our definition of Gibbs free energy is that it's the portion of the enthalpy that's the maximum amount of work that could be done. It's the maximum amount of work that could be done as electrical work or nerve conductions or muscle contractions. Remember, there's the other portion that has to be heat released into the universe. It has to be increase in entropy change. If we rearranged our equation, our delta G equals delta H minus T delta S, and we added T delta S to both sides, we see that the enthalpy change, the delta H, part of it is that delta G, which was our maximum work, And then the other part is the entropy change, and this is just the heat released as entropy. The question asks us how much heat will be released as entropy. Well, first it says that it's going to be 1 mole of hydrogen gas. And the equation, remember, said we had 3 moles of hydrogen gas. So we're going to use 1/3 of our final product. Then we multiply that by the temperature, 298.15 Kelvin, and the entropy change that we found before in step C. That was 214.8 joules per mole Kelvin. When we multiply that all out, we find that the heat is 221,348 joules, which if we convert to kilojoules is 21.3 kilojoules. So when we originally did our enthalpy calculation, we found that delta H for the reaction was negative 256.0 kilojoules. But this question here was talking about 1/3 of that because we're using 1 mole of hydrogen instead of 3. So if we divide 256.0, we find that 85.3 kilojoules would be the enthalpy change for the reaction. And we calculated in this step before that the maximum work that could be done, the delta G, was 63.9 kilojoules. And then here we found that the entropy change that must occur is 21.3 kilojoules. Alright, so say a reaction was going to power something, 85.3 kilojoules would be released, but only 63.9 kilojoules could be used. 21.3 kilojoules has to be released out into the universe as an increase in entropy. One more time, in this reaction, the molecules had potential energy in their bonds, and when all the bonds rearranged, the energy of the products was less than the energy of the reactants. 85.3 kilojoules of heat was given off as enthalpy, but only 63.9 kilojoules could do work, and 21.3 kilojoules had to be released as entropy. Remember when we learned about entropy on day 2 and we learned about the steam engine engineers that were trying to figure out how to make their engines more efficient, but then they discovered that some of the heat energy could not be converted to work, that some had to be released out into the environment as entropy. Well, this is just a chemical example of the same phenomenon. This is why the entropy of the universe is always increasing. We said that the power of Gibbs free energy is that it can predict whether a reaction will be spontaneous. We saw that delta G negative is a criteria that the reaction can proceed spontaneously to the right. So that means conversely, if delta G is positive, if delta G is greater than 0, the reaction can proceed spontaneously to the left. And then when delta G equals 0, this is the definition of the system being at equilibrium. So the quantities of A and B do not change. What that means is there are some molecules that are going from left to right and some that are proceeding from right to left, but overall the quantities of the reactants and products do not change. The thing is, the sign of delta G tells us from a thermodynamics perspective whether a reaction can take place. It doesn't say whether it will take place at any significant rate that we could observe or that it could overcome the barrier to get started. So maybe rusting, when a metal rusts, that could be thermodynamically likely to proceed, but it might take place at a rate over years and years and years. So it might not be significant for you today in the lab. Also, the activation energy barrier might be so large that even though the initial and the final products are likely, there's just not any chance that it will happen. For example, If you had mixed hydrogen and oxygen together, they might not spontaneously combust until you introduce a flame to get it started. So when thermodynamics says no, it means no. But when it says yes, it means maybe. There's other things that come into play. Let's take this example. So we have some reaction. Doesn't matter what the reaction is, but when we do our calculations, we find that the standard enthalpy change of the reaction, delta H reaction, is negative 100 kilojoules per mole. And the standard entropy change of the reaction that we looked up from our tables and calculated with Hess's law is negative 0.2 kilojoules per mole Kelvin. Will this reaction be spontaneous at 200 Kelvin? To figure this out, we're going to find our Gibbs free energy, and we use our Gibbs free energy version of the second law of thermodynamics, which says that delta G naught equals delta H naught minus T delta S naught. We'll plug in our numbers, and when we put everything in our calculator, we find that the Gibbs free energy change for the reaction at 200 Kelvin is negative 60 kilojoules per mole. This means because delta G is negative, we can say that the reaction can proceed spontaneously. However, it doesn't say whether or not it will proceed spontaneously. We would need to look at kinetics, which is another chapter, to figure that out. Now let's take the same reaction, but this time we're going to run the reaction at 2000 degrees Kelvin instead of 200 degrees Kelvin, 10 times the temperature. Let's see if this changes anything. We start with our Gibbs free energy version of the second law of thermodynamics. Delta G equals delta H minus T delta S, just like before. And when we put in our numbers, that the Gibbs free energy change is positive 300 kilojoules per mole. So this means that the reaction cannot proceed spontaneously. Remember that this is for the reaction going from left to right, maybe A plus B yielding C plus D. So this reaction cannot proceed spontaneously in that direction. But if we go the opposite way, from right to left, then our delta G will be negative, and that could proceed spontaneously. So now we have the same reaction. Let's find the temperature at which it's at equilibrium when A plus B going to C plus D has the same rate going forward and backwards, so there's no change overall in reactants and products. Again, we start with our Gibbs free energy version of the second law of thermodynamics. And the key here is that, remember, at equilibrium, delta G equals 0. So we'll put that in our equation, and we'll substitute in our delta H and delta S because those don't change. Those are standard values. And now we just have to solve for T. We'll add T times negative 0.2 to both sides, and then we'll divide both sides by negative 0.2 kilojoules per mole Kelvin. They cancel on the left side, and the units kilojoules per mole cancel on the right side, and we're left with the temperature at which equilibrium happens is at 500 Kelvin. So below 500 Kelvin, the reaction can proceed spontaneously. Above 500 Kelvin, the reaction cannot proceed spontaneously to the right. As we just saw in the previous 3 examples, changing temperature can sometimes affect whether delta H or T delta S is bigger. So it's kind of like a balance between delta H and T delta S, which predominates on delta G. So when delta H and delta S have the same sign, changing temperatures can change the sign of delta G. If we look at the equation for a spontaneous process, we can see that temperature as well as the signs of delta S and delta H will affect whether or not delta G is less than 0, and therefore whether the reaction is spontaneous. There are some diagrams that are designed by Dr. Stephen Lower that can help us understand. For those of you who are visual people, I think this will help a lot. If you're not so visual, I hope it doesn't confuse you, but I'll take some time to explain what's going on in these diagrams. There's a bunch of information contained in them, and they're pretty useful. So these diagrams are talking about whether the reaction A going to B is spontaneous. Up arrows mean that the value is positive, like delta H is positive or delta G is positive, whereas down arrows mean that they are negative. Let's look at the graph first on the left. Notice that delta H is a horizontal line right here. That's because at all temperatures, delta H is the same. But if we look at the T delta S line, the green line, we can see that it is sloped. And the slope will change based on whether or not delta S is positive or negative. So positive delta S will have a positive slope. Negative delta S will have a negative slope. And temperature is always positive, so that won't change whether or not the slope is upward or downward. Notice also with the delta H that it is below the zero line, because in this case, the first case, we're talking about when delta H is less than zero and delta S is greater than zero. Now let's move over to the pictures on the right side. They show what happens in two different instances, low temperature and high temperature. Let's just focus on the low temperature first. Because delta H is less than zero, this means it's an exothermic reaction. So the energy of B is lower than the energy of A, and that's why the delta H has a downward arrow, and that's why the energy levels for B start at a lower level than the energy levels for A. On the right picture, at high temperatures, notice that the distance is still the same for delta H. The lowest level of A versus the lowest level of B is still the same as on the left picture. And B's lowest level is lower than A's lowest level. That's because it is exothermic. B is stable at a lower energy level than A is stable. Now let's talk about the entropy. Remember from the first day, we saw that when you increase entropy, the energy levels get much closer together. And that's why here in case 1, we're saying that delta S is positive. That is, there's an increase in entropy when you go from A to B. And you can see that because B's energy levels are much closer than A's energy levels. Let's look at the left picture first. Remember, temperature is directly proportional to how much energy there is available. And this pink box that we see describes how much energy. Say maybe this is, I don't know, maybe at 50 Kelvin. And at 50 Kelvin, we start filling up energy levels. And all the energy carriers, say these are gas molecules, they can choose to go on different energy levels. Well, say, and these lines are completely made up as far as scale, but say for the A molecules, they can really only populate the first energy level line here. So not really much to choose from. The entropy is really low. But when you go to B, there's all these possibilities for energy levels that the molecules can go to. So the entropy is much higher. Now, overall, when we look at the diagram, we can see that B has much more energy levels available, much more energy levels populated, and that means that B is much more likely to occur, that the reaction will spontaneously proceed to B. When we look at the picture on the right, we are increasing the temperature. So the pink box is much higher. Say maybe this is at 1000 Kelvin. We start filling up energy levels, and here you can see A has more possibilities for energy levels, but there's still far less possibilities than for B. So B is much more likely to occur than A. Let's go back to the graph on the left. This also talks about delta G, the overall likelihood. Delta G has a downward arrow, and we can see that delta G is down at all temperatures. That means regardless of the temperature, when delta H is negative and delta S is positive, the reaction will occur spontaneously. Delta G will always be negative. And the higher up we go in temperature, the even more negative it will be. And that also makes sense if we look at our equation, delta G equals delta H minus T delta S. Because here we're saying that delta H is always negative. And because delta S is always positive, this quantity of T delta S, we will always be subtracting something. This will always be negative. And because delta H is always negative and the T delta S will always be negative, delta G will always be negative. The next case, case number 2, talks about when delta H is negative and delta S is negative. This is the same case as when we did our sample problems for that reaction. We had a negative delta H and a negative delta S, and we saw that at lower temperatures, at 200 Kelvin, the reaction could proceed spontaneously because delta G was negative. But as we started increasing the temperature to 2000, we found that it could not proceed spontaneously because delta G turned positive. And then we found that there was an equilibrium temperature where delta G was 0 at 500 Kelvin. This diagram explains that. So again, remember the up arrows mean positive and the down arrows mean negative. Let's start with our delta H. Again, we have a negative delta H. So our delta H line here on the graph on the left is less than 0. It's below 0 because it's negative. On the pictures on the right, the delta H is a downward arrow. Notice that the first energy level, the lowest one for B, always starts below the first energy level for A because B is more stable. It has a lower energy level. That's what negative delta H means. If you proceed from A to B, you are at a lower energy level, a more stable state. Now let's talk about the negative delta S. So here we'll look at the graph and we can see the slope of the T delta S line is negative. Also, when we look at our pictures on the right, this time we can see that the energy levels are far closer together in A than they are in B. Remember, closer energy levels is higher entropy. So we're going from higher entropy to lower entropy as we go from A to B. Hence the delta S less than 0 or delta S negative. Remember, as we look at the diagrams on the right, the pink energy level box is corresponding to the temperature. So at low temperature, we have a lower energy than we do at higher temperature. And if we look at the left picture, at low temperature, even though the energy levels are closer together at A, they can still only maybe 3 or 4 of them can be populated. But for B, even though they're farther apart, we have a lot more of them to be populated, maybe say 10. So B is the more likely state. That means if we go over to our graph, delta G is downward on the left. Delta G is negative. That means that the reaction will proceed from left to right, going from A to B. Delta G is less than 0. On the picture on the right, we have increased the energy as the pink box has gotten higher. This time when we compare the amount of energy levels, A has more energy levels available to be populated at the same energy as B. So this time A is the more likely state, and so the reaction will not proceed from A to B, it would proceed from B to A. And as we go over to our graph, we can see that delta G this time is an up arrow, and that's because delta G is positive here. So the reaction will not take place. If we go back to our equation, delta G equals delta H minus T delta S, we can see that the delta H is always negative and the delta S is always negative. But since we're subtracting a negative, there's a point at which these two will be equal. So that's the equilibrium point. And it's a temperature that makes that equilibrium point, because temperature magnifies the quantity of T delta S. And if we go back to our graph on the left, remember we're subtracting the two lines, delta H line from T delta S line, and all that's saying is looking at the distance between them. And There's a temperature, a crossover point, when delta G equals 0, and that is the equilibrium point. There are two other cases, two other possibilities. The first one we looked at was when delta H was negative and delta S was positive. The second one was when delta H was negative and delta S was negative. The third possibility is when delta H is positive and delta S is also positive. And the fourth possibility is when delta H is positive and delta S is negative. These are in your notes. I'm not going to go through them here, but I'd like you to try to analyze them on your own, and then we can talk about them in class. Let's talk about our review. So this concept map is also by Dr. Lower. Today was a big day. We talked about Gibbs free energy. Remember, this isn't actually energy. It is a state function that expresses the spontaneity, whether or not something will be spontaneous, whether a chemical process will be spontaneous. And it is the quantity of non-PV, non-pressure volume expansion work that a system can perform. That was like osmotic work or electrical work or nerve conduction potentials or muscles contracting. The spontaneity, whether or not it's spontaneous, is in terms of the enthalpy and entropy change. Remember, that's our equation, delta G equals delta H minus T delta S. It's under the conditions of constant temperature and pressure in the surroundings. That's like our normal laboratory conditions. And it's also called the Gibbs function. The definition is G is H minus T delta S. It is based on differences in the standard free energies of formation of the reactants and products, where delta G less than 0 or delta G negative means the reaction proceeds to the right, and delta G positive or greater than 0 means the reaction proceeds to the left, and delta G equals 0 means the reaction's at equilibrium. Also remember that delta H and delta S are standard values, but the delta G is temperature dependent. So as we raise or lower the temperature, G changes. And that's revealed by plots or graphs showing delta H and T delta S. And that at equilibrium, delta G will be equal to 0. And if we plug that into the equation and divide both sides by delta S, we get that the equilibrium temperature is delta H divided by delta S. We'll see that in our homework. All right, I hope you liked today. Today is a super important day, and please learn this information inside and out.